This video is maybe a little more, explains a reaction that's maybe a little bit more complex in terms of the mechanism than I would ask you on a test. But I want to show this to you anyway because it shows you how you can start to put the reactions we learned in this chapter together to make really magical things happen. In this example, we're making a ring. We're creating a ring. Now, we've only learned one other way to do that in all of organic chemistry that we've learned so far, and that was the Diels-Alder reaction. Making rings, first of all, making new carbon-to-carbon bonds is special in itself because it creates new shapes that will fit into new receptor sites. And so it'll change the environments where a molecule can be active. But forming a ring is really special. If you're making new carbon-to-carbon bonds to form a ring, it's really special because rings have a very rigid, reliable shape, and so you see them all the time in biologically active molecules. So being able to create rings is an opportunity to be able to create really biologically active molecules. As you transition into biochemistry, you'll see living things do this all the time. It's interesting to be able to do it as an organic synthetic chemist in the laboratory also. And seeing how it's done will give you hopefully a better understanding of how living things do it when you transition into biochemistry. So the reaction that we're going to draw the mechanism for here is called the Robinson annulation. Robinson was a chemist who figured out how to do this, and then the annulation is coming from the Latin word for a ring. I like to remember it. Annulus is the Latin word for ring. I like to remember that because it kind of shares a root with anniversary or annual. The year is a circular thing, sort of like a ring. And so an anniversary is something that happens when you go all the way around a year, all the way around the ring of a year. And so when you create a ring in this way, you're doing an annulation. Now, the general process that we're going to do is we're going to do first a Michael addition reaction, and then we're going to do an aldol condensation. And if you look at these molecules and kind of squint, that should make sense. After all, what do you see here? You see an alpha carbon, alpha to 2 carbonyls. That means that this can lose a hydrogen, become a nucleophile, and be a weak nucleophile. A weak nucleophile that would prefer the beta carbon, which we have here. We have an alpha-beta unsaturated ketone. And so we know that the carbonyl carbon is slightly positive, but also this beta carbon is slightly positive because of resonance. And because we have a weak nucleophile here, that's going to prefer that beta carbon. So you could see how you would do a Michael addition reaction there to create this new bond. On the other hand, notice that we have a ketone here. The alpha hydrogens here are acidic. That can turn into a strong nucleophile and attack the carbonyl here. Give you a beta hydroxy ketone, and then when you heat it up, you'd end up getting the alpha-beta unsaturated ketone. That's the aldol condensation. So overall, sort of just drawing a game plan, we would take these two molecules, and first we'll do a Michael addition that will connect this alpha carbon to this beta carbon, so that we'll have this sort of intermediate here. So notice we've created this bond between the alpha carbon and the beta carbon. Alpha carbon here, and the beta carbon of the unsaturated system. That's a Michael addition. And then once we have that, we can do an aldol condensation here. So you do the aldol condensation and you'd end up with your product. So that top part is already made. It's just here. You would form the new bond there. This alpha carbon acts as a nucleophile and attacks that carbonyl so that you form this new bond. At first you have a hydroxy group on this beta position, but then you do the elimination and you form the unsaturation. So those two connected to each other are called the Robinson annulation, and they're a way to create a ring. So that's an exciting thing. So let's walk through the steps for this one by one with all the curved arrows. If you want to settle down in your seat, it'll be quite a ride. So we'll start first, and it'll take a little time. So let's start first by having this, drawing in that alpha hydrogen, the acidic alpha hydrogen. That's acidic, and we're treating this with a base. That's the one thing we have. We have a base and heat. So the base, hydroxide, will swoop in, steal the hydrogen. The electrons will snap back onto the carbon there. So that's a proton transfer. Should seem really familiar. Compare this to the first step in, for example, the malonic ester synthesis, or the acetoacetic ester synthesis. So that creates a lone pair on that alpha carbon. Now that's a nucleophile. It has a negative charge, but it is weak because this is allylic to both of these carbonyls. So the charge is being spread out over all 5 of those atoms through 5 separate parallel p orbitals. Because that is a weak nucleophile, it will attack the beta carbon on this other molecule that they give us. So remember that when you have an alpha-beta unsaturated ketone, the beta position is slightly positive, right? Carbonyl carbon, alpha carbon, beta carbon is slightly positive. The carbonyl carbon is also slightly positive, but a strong nucleophile would prefer to attack there. Weak nucleophiles prefer to attack on the beta carbon. This is a weak nucleophile because its charge is being spread out over all 5 of these atoms. So it's stabilized, and another word for stable is not very reactive, therefore a weak nucleophile. So this will swoop in and attack that slightly positive beta carbon. At the same time that happens, this moves over toward the slightly positive carbon there and pushes these pi electrons up onto the electronegative oxygen. So what we have after that step is a new bond between the alpha carbon and the beta carbon. So I'll put that in purple here. This pi bond would have moved over, and this pi bond would have moved up onto the oxygen there. And so we have this new bond that we formed, and we have an enolate. Now the enolate, we don't have any hydronium here, so we can't do it using an acid-catalyzed mechanism, but we do have some water, after all, in this first step. The hydroxide stole an H+, and so we have some water in this solution. So the fully negative oxygen can do a proton transfer, steal one of the slightly positive hydrogens here, and the electrons in the bond would snap back onto the oxygen and give us our hydroxide back. So what we have after that step would be this here. And so at this point we have, oops, I'm sorry, mix this up. What we have here is, that does happen, that oxygen does steal a hydrogen, and you can have an enol at the same time, but the enol is also losing its hydrogen again, and so it's in equilibrium with the enolate. So that is one possibility. At the same time, the other thing that could attack that hydrogen is this pi bond here. So another place where these electrons can go is they can be attracted to this slightly positive carbon. They can push down to create a pi bond, and then that puts a pressure on these pi electrons here to stick to something positive nearby, which could be that hydrogen there. So in that example, after that step, we would have pi bond reforming in the carbonyl, and this now has its hydrogen here. Now I'm not going to draw that hydrogen in, it's implied in the skeletal structure, so that's what we have at this point. And so that is the first part. That is the Michael addition. That's what we just accomplished. This is the molecule we just have now. And we did that just by creating that alpha carbon nucleophile, reacting it as a weak nucleophile with a beta position of the alpha beta unsaturated ketone. And once we had that, this pi bond was forced to become electronegative, or was forced to act as a base by the instability of that hydrogen there, which existed in equilibrium with this enol. You wouldn't have to draw the enol if you don't want to. The essential thing, the thing that really changes this molecule, is that you get this. Note, though, even if you do form the enol keto-enol tautomerizes to give you the same product. Okay, so we've done the Michael addition. Now we can do the aldol condensation, the second step. So here, we still have base in this solution, and you'll notice we have this alpha hydrogen. We have the alpha carbon here, and an alpha hydrogen on it that's slightly acidic. So we can take another hydroxide, full negative charge. The negative oxygen here could steal that hydrogen. The electrons snap back onto the alpha carbon where they're stabilized through resonance. So what we end up with is a full negative charge there on that alpha position, and that feels the slightly positive charge on the carbonyl next door. You'll notice this, unlike our original nucleophile, this was a weak nucleophile and so preferred the beta carbon of an alpha beta unsaturated molecule. This only has one carbonyl that's helping to stabilize it. So it's a strong nucleophile and it prefers carbonyls. So the one that gives you the most stable bond angles in the ring is for it to attack this carbonyl here, and it kicks those electrons up, the pi bond, up onto the oxygen. So now you have your original six-membered ring. You have the carbonyl on top, the methyl group. You'll still have an O here, but it'll be an O with a negative charge, this carbonyl. Now let's think about what type of a ring we're forming. We have 1, 2, 3, 4, 5, 6 carbons in this ring. So we're going to have a six-membered ring. So that gives us 1, 2, 3, 4, 5, and 6 carbons. On carbon number 4, we should have the carbonyl. And on carbon number 6, we have the oxygen that becomes just a single bonded oxygen there. So it's sort of like an aldol addition. We have this nucleophile attack that carbonyl electrophile. Then we can take a water molecule, do a proton transfer to stabilize that. So the negative oxygen steals the slightly positive hydrogen there. The electrons snap back onto the oxygen. So we have a hydrogen here. So now we have this beta hydroxy ketone. You'll remember that that's the product of an aldol addition, right? This is the carbonyl carbon. Next door to that, you have the alpha carbon. Next door to that, you have the beta carbon. So beta hydroxy ketone, because you have this hydroxy group on the beta carbon. And if you heat that up, then that undergoes an elimination reaction because you have yet another alpha hydrogen here. So hydroxide can swoop in, steal that alpha hydrogen. The electrons can snap onto the alpha carbon there, where they're stabilized through resonance. And although it's stabilized through resonance, if you heat this up enough, it will compete for this slightly positive carbon. And what you can do is have that lone pair scooch over and kick this hydroxy group off, so that you end up with the alpha-beta unsaturation. And you'll notice that that was the final product that we wanted to explain making way back a million years ago, this product right there. So in this Robinson annulation, the mechanism for which is really long and complicated, in the Robinson annulation, you see the power of connecting these separate reactions to each other. Nothing new. There's nothing new in this video. You've seen the Michael additions before, and you've seen the aldol condensation before. All you're doing is putting them together. But you design molecules in such a way that you can form these rings in them. And features that should stand out are these 1,3 carbonyls. When you have those, you can use that carbon in between as a Michael donor, as a weak nucleophile that could attack a beta carbon, and an alpha-beta unsaturated aldehyde or ketone. Those features should seem familiar and remind you of these reactions. So you can use this alpha-beta unsaturated ketone in part of a Michael reaction, and if you want to form it, you can form it from an aldol condensation. So, complicated though it is, I wanted to show this reaction to you so that you can see the power of sort of putting these reactions together, and so that if you see a reaction like this in your biochemistry class, you would have seen it before at least. But like I said, this is more complicated and involved than something that I would expect you to do necessarily on a test that I give you for this class.